It's harder.
So the last thing we looked at, if you remember, we looked at basically like an XH2 where it was linear. Now we're going to make it a little bit harder. We now have an XH2 that is in a multi-dimensional configuration. So we're going to look at water or a bent configuration. So we want to go back through and we want to say, well, what is the point group of water? And it's going to be a C2V. So we look up the C2V character table. And so, of course, we're orbital-wise, we're limited to symmetries that are on this character table. A1, A2, B1, B2. So, of course, again, the number in each column tells us what happens under each symmetry operation. Let's see. Most of this is pretty well readable. Let's see. We also can determine degeneracy based off the characters in the columns. This one, everything is like single degeneracy. That again, that comes into play where you get, for example, an E symmetry. That'll be two degenerate. T will have a character of 3, so on and so forth.
When you say the -1 means the orbital changes, is that just the axis change and then it like?
Let's actually look at that. Okay, so let's just go ahead and start with the orbitals. And you'll see that once we get to like the p orbitals. Okay. So your s orbital is all just positive 1s. So if we look at water, so we're looking at the central atom now. So we remember our s orbital. Let's look at the symmetries on this. Okay, well, if I perform an identity on it, I'll get a 1. If I perform a C2, I'll get a 1. Because again, like I can rotate this all I want. It's not changing that orbital. Let's see. Do we remember which way our sigma V points?
Or sigma V?
Sigma V.
It'll be like in between those hydrogens.
Yeah. So your sigma V.
I guess is the V prime. No, the V prime goes down the bonds, right?
Yes.
Okay.
We just want to keep reminding ourselves of where these things are. So of course our sigma V splits the atom going straight between the 2 hydrogens, and then our V prime will go straight along the. Are we lagging? There it is. Yep. Yeah, our internet connection's unstable. That's awesome.
That always happens.
We have good connection on here. Okay, so let's look at what we mean by like a -1 changes the orbital. Okay, so well, first off, let's assign the symmetry of the 2s orbital. If we have 1, 1, 1, 1 all the way across, that's going to be an A1 symmetry. Okay, now let's, for example, Let's look at the PZ orbital. Now, you tell me real quick, which way do you think the PZ orbital is going to point?
It's gonna be up and down.
Yeah, because remember the z-axis is going to align along that principal rotation axis. So what we can, let's go ahead and put that in here. So do you see how, so of course, you know, p orbitals have different phases. So if I do anything that causes those phases to flip, that's a -1.
Okay. Okay.
So that's what we mean by changes the orbital. So if I look at this one, E is going to be a 1. Let's see, my C2 will still be a 1 because, again, that orbital is just going to spin infinitely. My sigma V isn't going to change anything. That's a 1. Sigma V prime will leave the orbital just as it is. I get a 1, so I have another A1 symmetry. Oh, sorry for the connection today. Oh, I drank all my coffee. Okay, let's look at the other two now. Let's do PX. Okay, let's have X. So we're kind of thinking of an axis like this. See, it'll pop up here in a second. There they are. So that means our PX, not straight line. It's going to go forwards and backwards. Try and imagine that as going into the screen, coming out of the screen. So now things are going to change a little bit. E, of course, are going to give us a 1. C2, what is it going to give us?
A -1.
-1. Because you see that C2 is going to flip the phases. The sigma V is going to go right down that orbital, so that would be a 1. Sigma V prime will give us a -1. Because the sigma V prime will flip those. So if we have a 1, -1, 1, -1, that's going to give us a B1 symmetry. And then last, we'll look at PY. What space do I have? I'll have to work in the ligand group. All right, so PY. We'll go side to side. So our E will be 1. C2 will be a -1. Sigma B will be a -1, and sigma B prime will be a 1. So this gives us a symmetry of B2. So that gives us the symmetries of the orbitals on the central atom. And of course, these are all 2px, 2py, because of course it's oxygen. We know where it's at on the periodic table. But our ligand group, okay? So took up more room than it should have. So what we're going to do, so our ligand group, so we have the two hydrogens down at the end of those bonds. So let's say we have, I'm going to start here. Okay, and then let's think about our symmetry elements. Okay, well, let's say that I have a C2 axis. I'm going to have my sigma V plane. And my sigma V prime. Okay, so now we start asking ourselves what happens. So the first situation is where the ligand orbitals, because again, hydrogen only has the one S, the ligand orbitals are in phase with each other. E will be 1, C2 will be 1, sigma V will be 1, and sigma V prime will be 1, giving this ligand group, ligand group over 1 is going to be a 1 in symmetry. Now, if we draw this again, at this time, we change the phase of one of them. This time our E will still be 1. Our C2 will be -1. Our sigma V will be -1. And our sigma V prime will be 1. Ligand group orbital 2 is going to be P2. So we know the symmetries of the orbitals on the central atom and the symmetries of the ligand group. Now, we know that for now when we're making orbitals, we know that A1s have to pair with A1s and B2s have to pair with B2s. Okay, so one thing that tells us is when we look at the molecular orbital diagram, do you see any of these orbitals that are going to be a non-bonding?
I mean the B1.
The B1, it's not going to do anything. It doesn't match symmetrically. It's not in the right kind of position in order to form a. It's not going to form a molecular orbital. Okay, so I have the actual orbitals for water here. This first one.
Okay.
First off, what do you think the symmetry of this one is?
The symmetry of this one?
Mm-hmm.
You're talking about just that one on the left there?
Yep.
I would say that's probably the A1.
It is.
And that's so that would be the 2s and of the oxygen and then the LgO1.
Right. So let's see. We're going to get our LgO1. Then we're going to put in the 2s of the oxygen. And those two are going to combine. And so that's going to be an A1 mixing with an A1. And what we end up with is this overall sigma bonding character. Now let's look at the next one. what do you think about the symmetry for this one?
I'm gonna say that's B2 and that's the LGO2 and the 2PY.
Uh-huh. So what kind of bonding character does that have?
That's gonna, will that be a pi bond? That's a little bit pi bond, right?
Nope.
No.
So let's kind of look at what happens here. So let's do the I'm gonna bring this over. Get rid of that, get rid of that. We know that we have a B2 here. And so then we are going to take p orbital, or the 2py, so we have a B2 interacting with B2. So it is kind of out there. So I will tell you there might be a little bit of pi in there, but there's a more specific overarching bonding character here.
More specific bonding character.
So there might be a little pi. Well, you see, hydrogen doesn't really do pi character. Remember that?
Oh yeah, you're right.
So since each one of these is encompassing the entire bond, this is a more sigma bonding character. But of course, we get this unique wave function because we've now mixed s orbitals with p orbitals. Did you ever think about water as being inorganic?
I mean, it technically classifies.
It does.
It's.
Most people think of the molecules that are predominant to life. A lot of people think of those as being organic. But it's like,
Yeah, organic has a really specific definition.
Organic has to do with the carbon-hydrogen bond in particular. Yeah, we're getting a little more complex here.
All right. That's got to be 2PZ and the LGO1.
So what symmetries are we combining?
So you're combining the A1s.
The A1. And here's the thing. You can actually go through, this is going to have to be A1 because it's a combination of A1s. But you can go back through, you can see that the C2, it gives me a 1, the E gives me a 1, and both sigmas are going to give me a 1. So this is an A1 orbital, so we know it has to be the A1s that mix. But you were right. We now have the PZ. That mixes with the LGO1. The next one, look at that. But now pay attention. So that you can see it, I've rotated the water.
Right, it's on its
So
side.
you need to take account of where the C3 axis is.
That one's just the PX, right?
It is. So again,
It has no interactions.
yeah, we can say that our C2 is pretty much there. Yeah, so this one is our PX orbital, and it is our P1. That's the one that's not going to interact with anybody. And as you notice, when you actually calculate these, it pops right out there. Uh-oh. The book didn't give you these, but I was like, no, we're going to do this.
Shoot, okay. So I'm gonna guess that's gotta be like the 2PZ and the LGO2.
Not two.
No?
No.
Why?
Okay, so you see how if you disconnected that thing around, you see how you have a lobe on top that's the same phase as the two lobes coming out the bottom?
Yeah, I guess.
So those two lobes coming out the bottom have to be the same phase.
So they are interacting. Okay.
And then the lobe coming out the top is going to have the same phase. And they kind of interact, but more specifically, do you notice the node on the bond? What do you think we have here? So which LGO do you think it has to be if your two sides have the same phase?
LGO1.
LGO1. So we have our LGO1. Now we have this, kind of just look at the top and then the green in the middle. You have an orbital going up and down. What do you think that is?
That's the 2PZ.
It is. So we still have to have, we know that LGO1 is A1. We still have to have A1 mixing with A1. Let's see which way we think that.
It's just opposite. You just flipped your PZ.
Yeah, where do you think the shaded phase is on the PZ?
On bottom this time.
Bottom.
Okay. Okay.
So we still have an A1, but how do we actually label this molecular orbital? And it has to be A1. But look at it. Think about the nodes right in the center. And can I get a color here that'll show up? You see these nodes right in the center breaking those bonds?
Yeah.
What does that tell you?
It's antibonding.
Antibonding. So this is our A1 star.
Oh, okay. Okay.
Now let's look at the next one.
Okay. Okay.
Now look at the phases on the hydrogens.
Yeah. So LGO2 and 2PY, and it'll be B2 antibonding.
Yep.
Okay. I get it. I get it. I'm gonna draw that one.
So we'll do LGO2. And then, like you said, we're going to get our PY. But it's going to have its phases flipped. Now, we remember that LGO2 is a B2. This PY is a B2. What do you think we have for the symmetry of this molecular orbital?
That's the B2 antibonding, right?
Mm-hmm. B2 star. So the book didn't put those in there. I'm like, no, these are.
No, those are, I like those ones.
Yeah, because this one, for example, okay, I'm going to go with the order the book has it. The quantum mechanics actually disagrees a little bit, but the book has this one. No, dang it. Sorry. Technically, your B1 here would be your highest occupied molecular orbital, which makes this one. What does that stand for again?
Lowest unoccupied.
Molecular orbital. Yep.
So that's where there's no more antibonding.
Yeah, so this molecule's done. Now, can you construct the molecular orbital diagram?
Oh gosh, okay.
You have to go lowest energy to highest energy.
Okay, you said this is the PX is the HOMO. And then there's one that we just did with the Okay.
So let's go back through and look at some of these. You kind of have three right there, 1, 2, 3 in the bonding regime. What do you think is lowest energy to highest energy?
I would say A1 is the lowest.
Yep.
And then I guess that one's the lowest, the top left one.
Yep.
And then,
Now, look at the positioning of the orbitals. Head-on bonding is going to be lower energy than side-to-side bonding.
okay, so do we want to say that the top right one is the next?
Yep.
And then that one on the
Yep.
left there, and then that one?
Yep. So, okay, so we can go ahead and put those in. And so what we're going to have, let's do, so I'm going to go ahead and grab that one. And I'm going to grab that one. I'm going to go ahead and grab this fourth one, because we remember what it is. Okay, so this is our lowest A1. And then we have the B2, and we have our next, so that's our 1A1, that's our 2A1. And now this one, that's our B1. Okay. Then let's look at these. I already told you which one the LUMO is. So what do you think for these?
I guess that'll be the highest, the one on the
Yep.
left.
So then we're going to go kind of jump a gap here. Okay, so all right, now let's look at the orbitals from each. So, all right. Okay, so out here, where is this going to be? Kind of down here next to B1. Okay, so this is where we put okay, so we have LGL1 and 2. And on the other side, let's go ahead and put in the symmetries for these. B2, and then A1. And on the other side, this will get a little more complex than what you're used to. So way down here, we're going to put our 2s orbital. Now I know that has to be my B1 for my 2px. Then my other orbitals are going to go right in here. So of course, those will be my, just kind of the way this works out, this will be my A1 and my B2. So then we start saying what connects to what. Okay. Now I know I'm going to have an A1 mixed with an A1. And so there, and there. I also know that this A1 is going to have to hit that A1 there, there, all the way up. Okay, now the one you're gonna like, we have to kind of work on reasoning out. So when you look this one up, this A1 goes down to here, but it doesn't go all the way down to the other A1. Why do you think that is?
Because it's already full.
It's already full, and also it's not the P is not going to cross into the S regime.
P will cross into this regime.
Okay, so it also means that this A1 is going to have to supply energy to the antibonding. Let's look at our B. So our B1 is simple. It's just going to go straight across to the non-bonding. And then our B2 has to fill in for B2. And that's the crazy molecular orbital we're looking at.
Mm.
Is
Yeah,
it?
it's definitely more difficult than anything I've done.
Oh, yeah. Guess I could put that in the center easier. So to go ahead and fill these in. 2BZ, 2PY. The most important thing is the structure in the middle, that you understand how these molecular orbitals come together. And so that you can check yourselves, this is what we're looking at. And then you can see the construction of the individual orbitals going all the way up.
You put a jump there. Is that something I'd have to be able to predict
Which jump?
from the B1 to the B2 star?
That one, always remember there's going to be a nice jump. There's usually going to be a nice jump between bonding and non-bonding to antibonding.
Okay.
The place where like you can really model them like this as long as you're, I mean, the semiconductor, the jump will be a little lower. When you get into metals, that's where that gap is going to come way down. But until you get there, you really kind of want to anticipate a good jump between the bonding so especially between bonding, non-bonding. So here, if you just look bonding to non-bonding, you see a pretty good jump in energy. That B1, all of your non-bondings are going to sit in that middle area. So they're going to hover energetically between your bonding and your non-bonding. All righty. So looking at BH3 and CH4. Let's see. BH3. So sometimes go back through and verify this for yourself. This is D3H.
B3.
So this is a D3H character table, and we see our symmetries A1 prime, A2 prime, E prime. We have double primes of all those. So we have to start asking ourselves what's available for bonding.
Okay.
All righty. So let's see. So we remember that our principal axis is there, which makes this the Z axis. Okay, let's start looking at the symmetries of some of the orbitals. Okay, so I take I'm going to try to draw this on its side as best I can. Okay, and then I'm going to take and put my s orbital, my 2s orbital, right around boron there. And I start looking at the character table. Okay, so you do this one. What do you think this one is? Look at all of the operations you have up there.
Yeah. Yeah, this one's probably gonna be an A prime one.
A1 prime. Because you see your C3s don't change it. Your C2s, but do you remember where your C2s are?
Yeah, down each bond.
Yeah. So here's your C2s. Those aren't going to affect it. Sigma H, that's not going to, your sigma H, so this BH3 lies right in the plane of the sigma H. That's not going to affect anything. The improper rotation, so we rotate it through 120 degrees and then invert through the sigma H, we're going to get the same thing. And the sigma V's, which will go along each bond, they're not going to affect anything. So the next one we want to look at is our 2pz orbital. Okay. Okay, so we have our 2pz. So let's take account of some of the things we have here. Let's put that up there. That's our 2pz. We have our C3. Let's see, let's do C2 axis. Let's do or there be one line. We'll see if that connects. Close enough. There's our sigma H. Let's start taking account of some of these interactions. So C3, that's not going to change it. That gives you a 1. The E is going to give you a 1.
The C2 prime give me a -1.
Yeah, -1.
Sigma H -1. So A2 double prime.
Yes.
Yeah.
Yep.
Yeah.
So then your S rotation will give you a -1, sigma H -1, but your sigma V's will all be a +1. So A2 double prime.
Wait, I have a question.
Mhm.
If I'm doing like IR on this, because that one, the A2 double prime is IR active.
Mhm.
Would I be able to just like see then if there's any interactions with that orbital? Is that what I'm looking at?
No, the IR is going to be more for the bonds, not the orbitals.
Okay.
So you're looking at bond stretches or deformations.
Okay.
And that you would go back through and you would do the reducible representations, and then you would break those down to how many of each of those do you have, and then you'll subtract out the translations and the rotations, and you'll get a number of IR vibrations.
Okay, sure. So this is, okay, this is different. This is totally.
Yep, this is using the character table for a completely new thing.
Yay.
Okay, so that is going to be our A2 prime. We can do the next ones together.
Okay.
Okay, so I'm just going to go ahead and copy this off down. So our sigma H, and then we can think of all of our rotations. All right, so then what I'm going to draw in is, okay, so RPY, and RPX, okay? Now, start looking at these. The C3, what does that give me?
C3 will give you an inversion. Well,
So just look at the 2PY. If I see three that, well, okay,
it kind of does a weird path thing.
it does.
You just want that it changes.
Okay, the first thing I want you to look at so you can get the C3 character, I have two of those together. What do you think this is going to have to be?
-1. What?
So yeah, your C3s will be a -1, but I have both the PX and the PY together.
Is there? Wait. Who do I think that's going to be?
Yeah, so look at your character table.
Oh, is it going to be one of the E's?
Yeah, it's going to be one of the E's.
Oh, okay, okay.
So then if we go through and we say, well, more than anything, let's take a look at the sigma H. Do I get a positive or a negative for the sigma H?
Sigma H. You're going to get positive.
So look at the character table.
So I guess we'll get E double prime, right? Wait, oops, E prime.
Yep, E prime. The others you can reason out. So the S3, if the C3 is a -1, the S3 is going to have to be a -1. And then your sigma V's, of course, are going to cause -1s. So this ends up having to be our E prime symmetry. Okay, we are out of time. We'll work on the ligand group orbitals next time and then continue on into methane. Then I'm going to jump ahead in this chapter a little bit because you can then reason out the rest of them in the chapter.
Okay.
But I just want to make sure you see how symmetry fits with symmetry as we get more and more complex.
Right.